the Western United States has an elaborate series of infrastructure, and that entire infrastructure was developed to capture snowmelt runoff. And so as we shift to rainfall, it's a totally different ballgame.
Hello, and welcome to the Water Buffs podcast. I'm your host, Mitch Tobin, director of the Water Desk. I'm excited to be speaking today to Noah Molotch, director of the Center for Water, Earth Science and Technology, CWEST, at the University of Colorado Boulder, where the Water Desk is also based. Noah is an expert on the snowpack, hydrology, and remote sensing. We'll be talking to him today about the importance of snow, what happens between a snowflake falling and water coming out of your tap, and what the future may hold for snow in the American West. Noah got his bachelor's degree from CU Boulder, his master's from UC Santa Barbara, and his PhD from the University of Arizona in Tucson, where I used to report and where we crossed paths many years ago. CWEST is part of the Institute of Arctic and Alpine Research, INSTAR, which was founded in 1951 and does world-renowned research with field sites located across all 7 continents and the world's oceans. Although we're both based at the University of Colorado Boulder, the Water Desk is editorially independent from the university as well as our funders. I'm excited to talk to Noah about snow, a subject I find fascinating, and that is at the core of many Western water issues. Welcome to the show, Noah. It's great to have you on.
Thanks. It's great to be here.
Wonderful. Well, let's begin at the highest level. For starters, tell us why snow is so important for the American West's water supply.
Yeah, so about 70% of the water supply in the Western United States is derived from snowmelt. It's the primary water supply for about 60 million people here in the United States and about 1 billion people globally. So this is actually something that's important, not just in the Western US, but around the world.
Mm-hmm. And many people seem to be worried, scientists foremost among them, about the future of snow in light of climate change. What does the science tell us about what is expected to happen to our snowpack going forward?
Yeah, so a lot of the Western United States, we have snowpack occurring at temperatures that are very near the melting point. And so a relatively subtle warming in climate can profoundly change the amount of snow we have and the hydrology of the Western United States in general.
Mm-hmm. And a lot of people talk about climate change as if it's a future event, but clearly we're feeling the effects already. Are we already seeing evidence of a thinner and less reliable snowpack here in the American West and elsewhere?
Yeah, there are hundreds of long-term monitoring sites of mountain snowpack across the Western United States. The measurements began in the early 1900s. The best record is from around 1950 to the present. And the data from those stations that have been measuring since the 50s have shown pretty widespread declines in the total amount of snow that we receive each winter all across the Western United States.
And are there interesting or notable variations across the West, or is it kind of uniformly the case that snowpack is declining?
So the Pacific Northwest in particular has seen the largest declines in mountain snow accumulation since 1950. But the last 20 years, we've seen those declines more dramatic in the Southern Rockies, for example, in Colorado, and in the Sierra Nevada mountains as well. So really, it's now a signal that's very clear across the entire West, with some variations in terms of the overall magnitude of how much snow has been lost.
So this last winter was kind of interesting. Here in Colorado, the snowpack was more or less average, but when it came to runoff and what reached the rivers, that was quite below normal. Tell us what was happening this past season to our snowpack and then the runoff that is so important to rivers?
Yeah, so this was an interesting year in that we had a relatively average snowpack, as you said, for Colorado. And um, what we saw in April was some snowmelt rates that were around double the average long-term snowmelt rates for April. So we had a relatively rapid snowmelt season, and that corresponds with an increased drying of the land surface through the summertime. And interestingly, this was a pattern that was seen across much of the western United States. The Sierra Nevada mountains in California also had very rapid snowmelt in the month of April. And so it's something that we're actively looking into as to what the climatic drivers of this um, anomalous snowmelt season, what was driving that. We're not really sure yet. It's relatively a recent event, so it takes us a little time to dig into the data and figure out what was going on.
Mm-hmm. Yeah, it seems notable that you can have an average snowpack season, but that doesn't necessarily translate into an average season as far as the volume of water making it to streams and rivers. So, pretty interesting scenario this past season.
Yeah, you know, when the snow melt leaves the snowpack and goes into the soil, it has, a few different pathways it can take. It can be transpired back to the atmosphere by plants and trees. It can recharge aquifers in the ground, and it can flow into streams. And the science that is involved in which pathway the water takes is actually quite complex. But in general, what we expect when we have drier than normal conditions in the spring and early summer is that more of the snowmelt will be partitioned to the atmosphere in the form of that transpiration by plants and the forest. And we haven't yet been able to identify whether or not that was an anomalous flux this past spring, but historically, that's how that usually plays out.
Mm-hmm.
And one of the things that's interesting about this, just to kind of add another tidbit on this, is that when we tend to have shallow snowpacks, we tend to see them melt earlier in the year. And when we have relatively deep snowpacks, we tend to see them melt later in the year. And then when they're relatively average, we tend to see the snow kind of melt on a trajectory that follows more of the average pattern. And so to see a snowmelt trajectory that was quite rapid and early in a year where the snowpack was actually relatively close to average is really actually a unique situation and can throw water managers kind of off guard because they're expecting a certain outcome based on how much snow's on the ground at the beginning of April. And by the time we get to mid-May and into early June, we're seeing an outcome that's actually quite different than what we would have expected based on what we were seeing in early April.
Interesting. Yeah, it seems like the forecast really changed pretty significantly, and I would imagine that's very challenging if your job is to manage water and to be uncertain about what's coming down in terms of the snowmelt and the runoff. So let's talk about measuring the snowpack. I think a lot of people have experience going in their backyard, taking a ruler and measuring how much snow has fallen. But as scientists, you're using much more sophisticated techniques. It seems like a challenging task. How do we actually know how much snow is out there?
Yeah, so not all snow is created equal in terms of how much water it stores. Just measuring the depth is not enough. And so most of us in Colorado are familiar with the idea that we can have light, fluffy champagne powder, and that's not going to have very much water in it, versus having some really wet, heavy snow, where of course that would produce quite a bit more water. And the depth of those two different snow conditions might actually be the same, but we could get very different amounts of water from the same depth of snow. And so we use a combination of ground measurements, measurements from satellites, measurements from airplanes, and computer models to try to estimate how much water is stored in the snowpack across the landscape for all of the major river basins that flow through the state of Colorado and really across the western United States. And so the measurements that many of us are familiar with in terms of just measuring depth, to get to the actual amount of water that's in the snow, we also have to know something about the density of that snow. Basically, how heavy is that snow? The mass of the snow or the weight of the snow is really what determines how much water's in it, not so much the depth.
Mm. Yeah, fascinating. And it's interesting how any skier or snowboarder knows that there's a big difference in the experience, whether you're dealing with that light, fluffy, as you mentioned, champagne powder, as they call it, versus that really dense snow I've heard it referred to on the West Coast as Sierra cement or Cascade concrete. Very, very different snow, certainly if you're skiing or snowboarding, but also from a water supply perspective.
Yeah, skiers and snowboarders actually have a lot more insight than they might realize about what controls the water supply in the Western United States. In fact, my background before I got into science was coming at it from that sort of recreational perspective, and it adds a lot of actually valuable insight.
Hmm. Yeah, likewise. One of the reasons I'm so interested is from that recreational standpoint, not to mention the water and other influences. So, talking more about how we measure the snowpack, if you go skiing, very common that the amount of snow in different parts of the resort will be sometimes dramatically different depending on whether you're at the base, whether you're at the top of the mountain. The wind can have a big influence. Even on a single ski run, the snow can be much different on one side or the other, depending on all of these factors, the wind, the terrain, the elevation, things like that. So that seems to be posing challenges in terms of how you measure snowfall across this enormous landscape when it's so heterogeneous and variable. So how do scientists deal with that?
Yeah, it's a really good question. And so all of the nuances that a skier might apply to thinking about what run they're going to ski next based on the conditions, based on where the wind's blowing, based on if it's the spring, how sunny it's been. And so maybe they're looking for corn snow where the sun has been warming up the snow a little bit. Um, and when we think about the variations from even one side of a ski trail to another, right? Like being in the wind-loaded area just on the leeward side of a stand of trees on the edge of a ski run versus the other side of the ski run that might have wind scour. We actually bring computer models and measurements to bear to resolve that kind of variability. And we do that by having first a digital representation of the topography. And we now have the ability to create that digital representation at a very high level of spatial detail. So at about like 3 meters horizontal resolution in terms of the way that we're discretizing the landscape. Similar scale of measurements in terms of the vegetation. And then we bring that kind of information into a computer simulation, which can position the sun in the correct location for the very minute of the day, and for every day of the year, so that the sun's moving higher in the sky as we move closer to the summer, lower in the sky as we approach winter, and simulating the full energy budget of the snowpack, simulating how wind is redistributing snow across the landscape as it falls from the atmosphere, and even after it's fallen and redistributes in the days subsequent to that snowfall. So all things that a skier might think about in terms of finding the best possible conditions for a ski run. And we do all of that in a historical sense to try to improve our understanding of the physics as to how this all works. And in a historical context, we can compare those kinds of models with detailed measurements for things like airplanes. And now increasingly we're using drones to collect this kind of information. And so that if we can compare what was reality based on these detailed measurements versus how these models are doing and learn how to improve those models, then we can do things either in real time that can be used then by water managers to estimate how much water's on the ground. And we can do things like play around with various climate scenarios as to how, if in the future the temperature warms by 0.5 degree Celsius or a full degree Celsius, how will these snowpack conditions change? So it's really a combination of bringing together kind of the historical past, the tools that we have to understand what's going on, and then using those tools to predict the future, whether that future is this upcoming spring and how much water we're going to get, or the future in 10, 20, or 100 years from now.
It seems like scientists like yourself have just made incredible strides in terms of understanding our snowpack and using all of these different technologies, drones and drilling into the ground, satellites. What are some of the big unanswered questions in terms of snow and the hydrological implications?
Yeah, that's something I spend a lot of time thinking about, and I think there's one sort of very utilitarian answer to your question, which is that we still don't have a good method to actually measure how much water is stored in the snow everywhere across the landscape. We can send out a couple of engineers to make a measurement in one place. That's pretty easy to do. We can set up automated equipment to measure how much water is stored in the snow at one particular place. But to be able to measure the total amount of water that's stored in the snowpack across any of your favorite watersheds, let's say the South Platte, which flows through Denver, or the Blue River, which flows into Lake Dillon on the other side of the Continental Divide, we don't have a good way to measure the total amount of water that's stored in the snowpack. So this is a big open question. How do you collect that information? And NASA is big on trying to develop the technology to do that. The other big unknowns are the feedbacks. So in any sort of question that we have that relates to climate science, it often has to do with the question of, if we warm by X, then what happens to Y, and does that lead to further warming, or does that lead to cooling? And that's what we mean by a feedback, that you push something in a certain direction. Does it exacerbate the initial forcing, or does it push in the opposite direction? And when it comes to snowmelt, there are many different processes that are occurring, some which act as what we call a positive feedback, which further enhances warming, and other phenomena which actually push in the other direction and can counteract some of that overall warming. And so in particular, we think a lot about forests. And as we change the amount of snow that's on the ground and the timing and magnitude of snowmelt, what does that mean in terms of the amount of carbon that these forests take out of the atmosphere? Right? Forests in their growth process are assimilating carbon from the atmosphere onto the land surface. And that can cool the climate system and offset some of the increased carbon emissions associated with energy production and human activity. And so we're trying to figure out exactly what the magnitude of the arrows are in terms of, as we warm the climate, how does the forest respond in terms of the amount of photosynthesis and growth that occurs, and how does that feed back on the amount of greenhouse gases that are in the atmosphere?
Wow.
I should mention a second very critical feedback, which has to do with what we call the snow albedo feedback. So snow is bright and reflective. It's like air conditioning for the planet. It reflects a lot of the sunlight back out to outer space. And so a huge question is, as we warm the planet and reduce the spatial coverage of snow cover, how much is that going to act as a positive feedback to further warming the climate system?
This is Water Words, a fast explanation of a bit of water lingo. I'm Hannah-Lee Myers. Today's water word is return flow. In the context of agriculture, the U.S. Geological Survey defines return flow as drainage water from irrigated farmlands that re-enters the water system to be used further downstream. There are two main types of return flow: surface water return flow that stays above ground and rejoins creeks and canals, while groundwater return flow seeps underground into aquifers. This underground water may also eventually reach streams and rivers. Return flow usually refers to water from agriculture, but may come from a variety of sources, like mining, industrial or domestic use, as well as natural sources, like wetlands. Return flow from farmland often carries with it unwanted salts and nutrients that then enter the river system. However, under the U.S. Clean Water Act, all return flow from agriculture and the pollution it carries is exempt from requiring a discharge permit. So if you hear reference to return flow and you imagine water that's been used but then finds its way back into the water system, you're correctly imagining return flow. Now back to the Water Buffs podcast.
Let's talk a little bit more about the technology that you use to measure snow and do research. There's this whole system that's called SNOTEL out there. Explain to us how that works and what information it provides to us.
Yeah, so SNOTEL stands for Snowpack telemetry, and it's a network of over 800 stations across the Western United States that are directly measuring on an hourly basis the amount of water that's stored in the snowpack. And the way that it collects that data, the way that the measurement is made, is that it has a bladder that's about the size of a dining room table, or maybe a couple of dining room tables put together. And that bladder is recessed into the soil just slightly, so it just looks like kind of a big tin pan that's flush with the soil when you see one of these. And inside the bladder, it's filled with antifreeze. And the bladder is connected to a tube that goes to something that measures the pressure in the tube. And so as the weight of the overlying snow accumulates on top of the bladder and pushes on the fluid that's in the bladder, that fluid applies more pressure into the tube, and then the pressure transducer, which measures that pressure, can estimate the mass of snow that's on top of the bladder. We call this bladder a snow pillow. And if you go skiing around on some of the backcountry trails, just about anywhere in the Western United States, you might come across one. They're actually located to try to avoid that happening. They tend to be placed in areas that are unseen to the public. One, so that they're not an eyesore, but two, so that they won't be vandalized. But there are, like I said, over 800 of these across the Western United States, and they're all part of a network. And the telemetry, so in SNOTEL, the word tel is for telemetry. And so they're part of a wireless network system. So they actually communicate through telemetry to send the data back to offices of the Natural Resource Conservation Service, where the data is all brought together in their office in Portland, Oregon, and a centralized location, and it's made available on the internet basically in real time, so you can see what's going on as the data is coming in.
Mm-hmm. Yeah, it's really kind of helpful to know on that real-time basis if you do like to ski and can look at some of those sites and don't only have to rely on the snow that's reported by the ski resorts. And as you mentioned, it's the weight of that snow, and so there you're able to get at that issue of the snow water equivalent, the content as far as the water, and it's not really the depth that's so important, but it's the amount of water that's in there.
Yeah.
So you also mentioned aerial imagery, satellites and drones, I guess planes also. How do we know about the snowpack from these aircraft, or in the case of satellite, spacecraft that are so far from the snow itself?
Yeah, so this is, there is a long answer, but I'll give you the short one. I actually teach my class on this topic, but from the most simplistic measurement that we make from satellite in terms of snow is whether or not there is snow on the ground. So interestingly, when you look out of an airplane window, you can easily see snow on the ground versus vegetation or bare soil. And as a result of the unique sort of optical properties of snow, that it's so bright and white, we actually have a longer record from satellite of snow than any other water-related measurement that exists from satellite. If you look at the very first declassified satellite image from the TIROS-1 satellite in the early 1960s, about the only thing you can see that relates to water on the land surface is snow versus no snow. And we've actually been able to take just that simple observation of is there snow or not on the ground and do a lot with it. So one example, if you see snow persisting on the ground for a long period of time, long into the summer, you would intuitively have guessed that there must have been a lot of snow there to begin with, right? If it's not melting and disappearing quickly, then there must be a deep snowpack there for it to just keep persisting. And those of us who live in Colorado and look up at the Continental Divide, every spring and early summer, and we still see snow up there in June, July, we go, oh, well, it must have been a big snow year because there's still snow up there in July. So intuitively, we can convert the persistence of snow on the ground, how long it's there, into an amount of mass. How much snow must there have been before the snow melt began? And so this is actually something that I worked for about a decade on, was developing what we call a snow water reconstruction, where we watched the depletion patterns of snow from satellites that can just see whether or not there's snow on the ground or not each snow melt season. And based on how long that snow persists on the ground, and with some relatively complex computer models, we can recover an estimate of how much water was in the snowpack before the melt began. So even that just relatively simple measurement, snow yes or snow no, can be useful for some relatively complex methods for estimating how much water's there. Now we have, on the other end of the spectrum, new technologies using things like LiDAR, which the population is now becoming familiar with because some self-driving cars are being developed with LiDAR technology. These are lasers, basically, that would shine out from the car and measure the distance of the car to anything it might crash into. Well, we have lasers that we can put on airplanes, and we can point them down at the ground as we're flying over, and we can get a precise measurement of the distance from the airplane to the ground. And we can fly over specific areas in the summertime and get an exact height of the ground, and then repeat that same exact flight line in the winter time when the snow's accumulated on the ground. So now the ground is a little bit closer to the airplane than it was in the summer because the snow has built up on the bare ground. And then we can subtract the distance that we measure in the winter from the distance we measure in the summer. And that difference is the amount that the snow accumulated. And with that, we can map snow depth at very high resolution, so high levels of detail and space on the ground, and with a very high level of accuracy. So there's a program called the Airborne Snow Observatory, which has been around for about 8 years now. And it's allowed us to make very detailed measurements of the snow depth, which we can combine with computer models that relate to how heavy or dense the snow is, to give us a total amount of water that's in the snowpack. So those are, I think, two examples of very different technologies. One's very simple, just snow yes or snow no from satellite, and the other being, let's shine lasers out of airplanes, and eventually maybe we'll be doing it out of a spacecraft to measure the depth of snow on the ground.
Yeah, that's incredible. So the forecast for snow is something that's watched very closely here in Colorado and other Western states because of the water supply impacts, affects things like wildfires and certainly alpine sports. It seems like we know somewhat in the next week or 10 days whether it will snow or have some sense of it. And we know on a long-term basis that there's concern about climate change causing a reduction in the snowpack. But sitting here, we're talking in September. Are we able to get a sense and predict what this coming winter is going to be like as far as snow? In other words, how far out is our predictive ability go in terms of our skill at forecasting snow? It seems like we're pretty good at the scale of a couple of days or a week, but beyond that, it seems like a lot of people think it's just fantasy land as far as making forecasts for snow. How do you see that?
You're touching on what is the real challenge, right? Which is forecasting precipitation on kind of a seasonal basis. So I just noticed, because I follow Steamboat on Instagram, that they've announced their opening date is November 21st. And what I want to know is how much natural snowfall is there going to be between Halloween and November 21st. That's going to dictate the quality of the skiing over Thanksgiving this year and how much terrain they'll have open. And this is something that's very difficult to estimate. And equally difficult would be to say, well, by April 1st, how much snowfall are we going to have had? And there are parts of the Western United States where there is a statistical correlation between ENSO, or El Nino, and the amount of snowfall that occurs. So ENSO stands for the El Nino Southern Oscillation, and it has to do with the strength of the trade winds and the temperature of the eastern Pacific Ocean. So basically the waters off the coast of the northern part of South America up to Central America. And there's a correlation between those ocean temperatures and precipitation in the Western United States, broadly speaking. And the correlation is that when we have an El Nino condition, the southern tier of the Western United States tend to have above average annual precipitation, and the northern tier has below average. And when the conditions are La Nina, which means that the ocean temperatures in that region of the Pacific are colder than normal, then we tend to have below average precipitation in the southern tier of the Western United States and above average precipitation in the northern tier. So it's kind of a lever that dictates, if you're a ski bum, whether or not you want to move to Big Sky for La Nina and get the powder up there, or maybe Wolf Creek in southern Colorado, or Tahoe for the El Nino. And the reason I'm giving this long backstory is because Colorado kind of sits in between that fluctuation between the northern tier getting more precipitation during La Nina and the southern tier getting more in El Nino. There's actually not a strong statistical relationship between total snowfall for the winter and ENSO in Colorado. We can have big snow years when it's ENSO, or when it's an El Nino condition, and we can have big snow years when it's a La Nina condition. So, and vice versa, we can have low snow years under both of those conditions as well. So it's very hard to predict this for Colorado. Mm-hmm. And so I don't have a prediction for this upcoming winter, which is what a lot of times people want to know. My students, when they graduate in May, they're like, oh, I'm going to take a gap year before grad school, and I want to go be a ski bum. Where should I go? This is like the end of my snow hydrology class. This is what they want to know from me. And I usually tell them, well, you better wait until late November, early December, and then make the decision then, kind of see where the snow's flying. But yeah, it's very difficult to predict how much snowfall we're going to get when we're talking about sort of the 1 to 3 month forecasting horizon.
Mm-hmm. Yeah, and I guess there are some people who chase powder and just sort of live in the moment and go where the storms are and don't settle down because it is so hard to predict. And, as you mentioned, whether a ski resort is going to open for Thanksgiving, here in Colorado, that's a big deal economically as well as other parts of the region. Very important for that multi-billion-dollar industry and their finances and all of the associated economic activity. And in terms of El Nino and La Nina, we're kind of in, as you mentioned, here in Colorado, it's a more muddled picture, but it does appear that we are perhaps going into a La Nina now.
Yeah, that is, I think, what the data suggest. There are, forecasts of that, and that has to do with the difference in pressure in the tropics that drive the strength of the trade winds. And we don't know how strong or weak the La Nina condition might be at this point. But there does seem to be a La Nina condition that is developing in the Pacific.
Mm-hmm. And another question about Colorado in relation to other parts of the West, it being sort of intermediate between those northern tier and southern tier states. I've heard people say that there may actually be an increase in precipitation in the northern part of the country, and warmer air is able to, in a sense, hold more moisture, and that conditions are expected to be drier in the places that are normally drier in the desert Southwest. Here in Colorado, we're in the middle. Is that a helpful way to think about potential climate change impacts? That things might be wetter up north and drier down south, or is that the wrong way of thinking about it?
Well, so the first principle suggests that in colder parts of the planet, as the air temperature warms, that it may get wetter. But there are circulation patterns that can create winners and losers from that perspective, assuming that a winner is getting more precipitation. And in a dry climate like we have here in Colorado, it's actually pretty hard to forecast whether or not we're going to have more or less precipitation as the climate warms. And I think that there's somewhat of a dangerous perspective there, which is to say that as the climate warms and the landscape dries more rapidly, that will be rescued by the fact that increases in precipitation will occur. But our confidence in knowing that increases in precipitation will occur is very low compared to our confidence in knowing that the atmosphere is simply going to get warmer, and therefore the land is going to dry faster. So I would say that what you said is correct, but we need to be cautious in terms of then how do we interpret the risk of climate change as a result of the fact that, yes, some cold parts of the world will get wetter as the climate warms. We actually don't know which of those cold places will indeed get wetter. Not all of them are going to get wetter. On average, it's likely that cold places will get wetter as the climate warms. But on average, when you're talking about the global scale, is not very meaningful when it comes to thinking about real world decisions that affect ranchers and farmers and municipalities in a particular part of the country.
Mm-hmm. And I guess there's the crucial issue of whether the precipitation falls as snow or as rain, and it could be the same amount of liquid, but if it falls as snow versus rain has pretty important implications for the water supply, not to mention snow sports.
Yeah, and that's we didn't talk about that earlier, but that's really kind of a primary factor here to talk about when you're talking about climate change and snow. The reality is proportionally you're going to have more rainfall and less snowfall. And the Western United States has an elaborate series of infrastructure that's designed to store and distribute water to the 60 million people of the Western United States. And that entire infrastructure was developed to capture snowmelt runoff, right? And so all the operating procedures, all the methods we use to forecast the amount of water that's going to come, and then all the levers that get pulled to move water around are all relying on this snowmelt dominated hydrograph. And a hydrograph is a time series of stream flow. Sorry to throw out some jargon there, but it's basically all oriented around a stream flow regime that's dominated by snowmelt. And so as we shift to rainfall, and so then the rivers start pulsing in the middle of winter, whereas historically they had stored all the water and then pulsed only in the spring, it's a totally different ballgame in terms of trying to store that water so that it can be used for all the various requirements that we have as a society, whether that's for agriculture, hydropower, municipal use, in-stream flows for protecting habitat. These are all being managed under a relatively complex series of rules that are designed around snowmelt.
Mm. Yes, and this seems to be an issue that comes up a lot in water issues in the West, and this notion that we built all this infrastructure in the 20th century primarily, thinking that we would have the 20th century climate, but now we're in the 21st century and things are a lot different, not to mention that a lot of the laws and policies were created in the 19th century, so we have that sort of historical mismatch between the policies, the infrastructure, and the climate that we now have.
Yeah, it's interesting because we actually have some of the most talented water resource engineers in the world, and one of the most, if you look at the Western United States or California, other countries look to how we do things here. In terms of how to manage water in arid landscapes. And there are places that are, I would argue, are even ahead of us, like Israel and Australia. But we really have an impressive system for how we move water around the Western United States that allowed us to settle in this broad desert. And so on the one hand, we should be grateful, right, for all of the expertise that's there. But we also have to be careful about falling into sort of a rigid view that how we've always done things in the past is how they should be done in the future. And that kind of institutional stubbornness, if you will, that's maybe an unflattering word to use, but there's institutional memory in there, right? So somebody retires and then they train their replacement as to how things are going to be done. Their replacement may have just come out of university and have they might be bright-eyed and bushy-tailed about new ways of doing things and new data sets to bring on board. And so you do see institutional migration to new technologies, but it has to be done cautiously. So as a researcher, I have a lot of interest in seeing how stakeholders adopt new technologies. And they are relatively slow to adopt new technologies, and rightfully so, right? I mean, the stakes of them making a mistake, I can make a mistake in my research. It doesn't flood anyone's home or put a farmer out of business. And so these folks who are actually making real world decisions, they have a lot riding on these decisions. And so they are wise to be conservative in adopting new approaches. And I think that's kind of this interesting sort of ecosystem of individuals that we have in terms of researchers and practitioners sort of meeting together and discovering new ways that technologies can be brought to bear on problems that the practitioners are encountering. And so that's a big factor here when it comes to the changes in climate and the increased variability in climate. So we talk about how the climate's changing over time, but one of the things that practitioners are sort of struggling with is the increased variability in the climate. Not so much that the average condition is changing, but that the changes in conditions, the extreme conditions, wildfire is a great example this particular year, but how to deal with those extremes. And so we need actually more researchers who are listening to these practitioners that are explaining the sort of real world problems that they're dealing with related to these extremes, and then bringing to bear the new technologies and the research to address those kind of stakeholder driven questions. That, in my view, is really how we as a society kind of manage this and mitigate the impacts of climate change as they occur.
Mm-hmm. Yeah, that variability, and as you mentioned, the extremes, it seems like that's one of the most pressing issues is deeper droughts, bigger floods. I think of California and the Sierra Nevada going from one of the worst snowpacks in a century, and then soon thereafter, a huge snowpack and floods that almost took out Oroville Dam, and seeming like it's just going from one end to the other.
Yeah, we just published a paper on that Oroville spillway disaster event, and when you're coming out of the most severe drought in the historical record into one of the wettest years in the historical record, it is mind-blowing how challenging that is for the water management community and those that are responsible for public safety in the context of all of these dams and structures that we kind of take for granted or are there to improve things for us, but they can lead to some significant hazards. Luckily, the worst case scenario was averted in that particular case, but there were billions of dollars in damage to California's largest dam, and so that was not a trivial sequence at all.
Mm-hmm. Yeah. Well, this has been fascinating, Noah. Really appreciate you taking time to chat. Anything else that you want to let folks know about the snowpack and its future in the American West?
I would just say for people to think about little things that they can do with regard to energy consumption and fossil fuel combustion. That the reality is that anthropogenic climate change is real. It has an impact on things like snow, which is something that's near and dear to my heart. We should have as like a mantra for the future, is like blower pow for everyone. And by the way, it's going to keep the cost of all your produce cheaper as well, and keep the families that have been ranching and farming for generations going as well. So it's totally bipartisan. It's something that we just need to do.
Mm-hmm. Well, fingers crossed. I guess think snow, as they say, and hope this winter turns out to be a good one.
Yeah, absolutely.
Great. Well, thank you again, Noah. This has been really great. Appreciate you taking time to chat.
Yeah, thanks, Mitch. It was great.
Thanks for tuning in to the Water Buffs podcast, available in audio and video formats on most major media platforms. Water Buffs is a production of The Water Desk, an independent journalism initiative based at the University of Colorado Boulder's Center for Environmental Journalism. You can learn more about us and about water issues at waterdesk.org. We're also on Twitter, Facebook, and Instagram. If you have a comment or have a question, please feel free to email us at waterdesk@colorado.edu. Special thanks to the executive producer and co-manager, Hannah Lee Myers, and to our graphic designer and co-developer, Jeff McGee. Be sure to check out our other episodes, and until next time, thanks for tuning in.